Well, good afternoon. My name is Raul Olivera, and I'm going to present you the progress of my research project for my master degree program in applied chemistry. This poster is titled Graphenic C3N4 and BiOBr heterojunctions Preparation and Photocatalytic Performance in Microfluidic and Conventional Systems. This work In this work, we discuss the preparation of heterojunctions of graphenic carbon nitride and bismuth oxybromide for photocatalytic applications, like degradation of medicines such as amoxicillin. Also, we proved the efficient in the use of batch and microfluidic reactors in this kind of reactions. The microfluidic system shows superior performance in degradation of amoxicillin using these heterojunctions, reaching 60% of degradations in only 30 minutes. Otherwise, the back reactors achieve 30% of reactions in 5 hours. The preparation of pristine materials were made by two different methods: the thermal polycondensation of dicyanoamide to obtain C3N4. In this method, 10 grams of dicyanoamide is heated at 550 degrees to obtain bulk C3N4 and then is exfoliated with a heat treatment at the same heat to obtain graphenic C3N4. This method is better explained by Shagler et al. In 2021. On the other hand, to obtain BiOBr, we use the hydrothermal method, where bismuth nitrate reacts with potassium bromide in pressure conditions to get this semiconductor. Yang et al. Developed this method in 2010. The heterojunction preparation was performed with a novel simple process that we call photoanchoring. In this method, a mix of both material pristine with help of a photosensitizer like ethanol were dispersed in an ultrasonic bath for 10 minutes. Then, this mix is stirred with a normal stirring plate and irradiated with a LED lamp for 2 hours. This process helps us to put in contact both materials. This kind of heterojunction helps us to reduce the recombinations between charge carriers and enhancing the photocatalytic activity. To compare the enhancing of heterojunctions versus the pristine materials, we made photocatalytic tests of amoxicillin degradation. In this test, 50 ppm amoxicillin solution is irradiated in presence of the catalyst. This test was made with a 13 watts LED lamp. To monitor the degradation, aliquots of the reaction mixed was read with an UV-Vis spectrophotometer. This proof showed that the CNB 50 sample, 50% weight heterojunction, achieved 13% of degradation in 5 hours. The design of the microfluidic system was made by 3D printing lithography using UV resin as precursor. Then, the material was deposited as thin film in borosilicate substrate. With help of silicon, we montage the system avoiding fugues and create a single-channel laminar system. True, we passed the contaminant in presence of light to complete the photocatalytic test. This with help of a syringe pump and tubes. Microfluidic tests were made taking samples that pass through the system every 30 minutes with help of a spectrophotometer to monitor the percentage of degradation in a single pass. Each test was repeated to determine the efficiency of the system after 5 hours of use and reused 5 times, then was repeated with another film to determine if these results are reproducible. The best samples were obtained after longer illumination films, being the 300-minute samples the best in comparison. Additionally, we observed a decline in the degradation after the fourth cycle of their use. To determine the reaction kinetics and degradation mechanism, reactions were carried out at different flow rates. This experiment allowed us to determine the most efficient resident time for degradation, with 13 minutes of illumination showing the best result in the shortest time. Scavenging tests show us that the photodegradation of amoxicillin takes place downstream of free hydroxyl radicals generated by holes in the surface of the material, and to a less extent the oxidizing effect of the holes. As conclusion, we can say that the formation of C-scheme heterojunctions between carbon nitride and oxybromide significantly enhanced photocatalytic efficiency, reducing electron-hole recombination and increasing pollutant degradation. The CMB50 sample, 15% weight of carbon nitride, showed the highest efficiency in batch system, achieving 13% of amoxicillin degradation in 5 hours. The use of microreactors significantly increased efficiency, achieving over 60% degradation in just 13 minutes. I want to acknowledge the funding from Ciencia de Fronteras program and the city for providing my scholarship. Thank you very much for your attention.